What's up, class? This is round 2. This is a quick tutorial. Once again, I've done this in class, but now that you have it for video for later use, for you guys that are still working on tutorial 3, I'm just kind of a run through of tutorial 3, problem 3, I think it is. Let's see, yeah, problem 3, where you're working on input, user input, output, and it's a problem that is physics-based in terms of projectile motion. Okay, so I'm going to show you real quick in script inputs and outputs. Okay, so x equals input. This is the function input. Okay, and as you can see, you need to put prompt in there. And that's just basically it. And that prompt is going to be a string. Okay, and whatever the user enters after that prompt is assigned to the variable x. So x equals input. No, we're going to make this v for velocity. What is the initial velocity? Okay, and then I like to put a colon and then a space. Okay, and then that. Cool. And then a equals input. What is the initial? What is the launch angle? Okay, I think a cool thing to add is in degrees. And then put the colon, then the space, and then suppress it, and then this would be like meters per second. Okay, cool. So then we have that. We're going to run this as, we're going to save it. Now example. Okay. So what is the initial velocity? Meters per second, 9 degrees 40. Okay, and it's cool because now you have these variables a and 9. So you can always be checking this workspace area to see if what you're inputting is correct. Okay, cool. And this is going to be a quick tutorial because the bell is about to ring. Okay, so then you want to use that. Okay, and the big thing you want to do in this tutorial is the first step is to calculate the horizontal component of the velocity initially, and then the initial vertical component. First thing is the angle needs to be in radians for MATLAB to use it correctly. So do a times pi divided by 180. Cool. Okay, and then suppress it. Okay, so I'll just do horizontal x. Okay, velocity x equals, and then it's velocity times cosine of a. All right, that's a simple trig. I'm not going to go over that. Okay, so then I want to output it, and I like using f(f) output. It allows you more functionality, allows you more things. So once again, format spec, so that's where your script's going to be. A1 is the variable that you're plugging into that script. Okay, so the initial velocity in x direction equals, okay, and then percent to f. Okay, and then I'll explain what that means in a sec. Meters per second. Then you want to do \n, which means new line, and go over what all this means in a sec. And then the thing we're plugging in is v underscore x. That's the variable. Okay, and I close it. Okay. So what this is saying is it's going to print this script initial velocity in x direction equals, and then this whole thing is a holder for the variable. That variable is v underscore x. So this, whatever this is equal to, which is found here, is plugged into that. F is kind of designating the format, floating point number. 0.2 is 2 decimal places, or 2 numbers after the decimal place, so 2 to the right of the decimal place, and then percent is just part of that format. So once again, don't overthink this, but this is a holding place for that variable. \n starts the line. Okay, and that's important because I'll show you what happens if we don't do that. Okay, so now I'll go down here, run it. Example, what's the launch velocity? Initial velocity was launch angle, 40 degrees. Initial velocity equals x direction equals 30.64 meters per second. The problem is I didn't start a new line, so this is here. So now when I type whatever I want to type in the command window, it kind of looks funny because this is over here to the left like it normally is. Now we have more variables. We have v equals 40 and v underscore x equals 30.6418. Okay, so \n for new line. Okay, cool. And then now, so that's the first part you also need to do in the y direction. Okay, Then it's also plotting x versus y. And this is where people are really struggling. Okay, so the key is, if you bring your tutorial over, okay, is these kinematic equations. Okay, oh, there's all the answers. I didn't think this went through, but that's okay. I'm kind of giving you the answers anyways. Okay, but here's the kinematic equations. Okay, and this is what you need. So you're plotting x versus y. So you need to create a vector for x, and you need to plot the same size vector of y. So they need to be the same dimensions, but it has x values and y values. So you apply the motion. Okay, to be able to do that, you need a t vector. Okay, so the first step really is creating that t vector. And to find that, you need to find the total time within the air. Okay, so going back to our equations, we just have 4 minutes. Oh my god. What's up? I'm making a tutorial video. It's really awkward. You want my keys?
Oh, yes, please.
I'll get this done before class. So.
Which one is it?
The one that says any of them. Any of them.
Really?
Yeah, really. Okay, sorry. That was Ian getting food. Okay, so we need to find t. One thing you should know from physics is that the velocity at the apex in the y direction is 0. So we're going to use this equation here. So vy naught is the initial velocity in the y direction. Vy is 0 minus gt. Okay, ooh, we're definitely going to run out of time. So vy equals y equals v times sine angle. Okay, so then t equals v y divided by 9.8 or g. Okay, and then you multiply that by 2. I don't care about sound at all. This is for you, Ian. Okay, so now we have that time, and we're going to run this. Okay, so we're going to do example. Okay, and then what's the initial velocity? 40. Okay, so now initial velocity expression, and now we have a t, which is 5.24727 seconds. I didn't print it, but you see it here. You see it here. Okay, so the t, it's equal to 5.2472. So now I need to create, okay, a vector from limit space from 0 to t. And I'm going to call this vector time. Okay, this is where a lot of you guys are screwing up. Okay, so that's a vector now. Okay, and now I'm plotting x versus y. Okay, so I'm going to bring up this to show you real quick. And I'm going to make this equation and then this equation. Okay, and those are going to give me the x and y coordinates. Okay, so then, real quick, 2 minutes. Okay, x equals v underscore x times dot that. Okay, just remember that times time. Okay, y equals v underscore y dot times time minus 0.5 times 9.8 for g dot times time. Okay, squared. Let's see if this works. Cool. If it doesn't, oh well. Okay, so then I plot x versus y. Okay, so go down here, run example. What's initial velocity? 45. Okay, awesome. Voila. Okay, so this is x, this is y. Okay, and formatting won't be in this. But the key is, and a lot of people are screwing up, and I'm going to make a second tutorial to go over this, and other things, is that they are doing t. So they find t, they're like, okay, I have an equation for t, I just do this because that's what the equation looks like in the kinematics, right? T, and then they go to the plot, and they're all excited, and they're like, today's the day, it's going to work, 40, 45, and they come here, and they create this plot, and then bam, there's nothing on it. And why is that? Because you're just plotting a single point. You need to plot the vector. So right now, x and y are just 163 and negative 2 point blah blah blah. That's not a very good thing. So this is going to be time. That's the bell. I need to go to class and teach you guys time. Okay. And now when I run this, I'm going to do 45. Now we have two vectors applying the same here, which helps us so much. Okay. So now that class started, I can't do this, but I am going to create a second one that goes over how to format, because you need to create text boxes actually in it. Okay, and we'll talk about it in class. Cool. Hopefully this works.